Hello, this is Dan Alford with ARC Specialties. This is another in our series on designing for automation. People are worried about robots taking their jobs. I can assure you, if robotics was easy, my life would be easy, and it's not. So what we've done over the years is when we tackle a new job, frequently we have to change the rules in order to facilitate automating the project. We're talking about an interesting one today. This is pipe cladding. There's a phenomenon in the oil field called stress corrosion cracking. So in the deeper oil fields particularly, we have a H2S problem, or sour gas problem. So the oil is combined with sour gas, and if this sour gas contacts the steel of pipes or fittings and valves and such, what we have is corrosion and the creation of atomic hydrogen. The atomic hydrogen actually migrate in the grain boundaries of the steel, and then more hydrogens flow in, and you actually create gas pressure within the crystalline structure, and you get catastrophic failure under no load at all. So the way around this problem is you have to eliminate the iron, which is what the H2S combines with. So the pipe can't be made of iron, but steel is iron and carbon. And iron and carbon has a lot of advantages, very strong, very inexpensive and such, but we need an internal coating. So what you see here is an internally coated using gas tungsten arc welding. And the material that we've overlaid it with is Inconel 625. Inconel 625, very low iron, and it's impervious to the H2S. So when we first tackled this project, everybody was making their welds in this manner. And these are called stringer beads. You can see there's 1, 2, 3, 4, 5, 6 beads per inch. And this is traditional. And I think the reason that industry went this way is because we're trying to clad 40-foot long pipes on the ID, and these IDs can be all the way down to 5 inches. And so you need a torch that's extremely long. And one way to do this is, rather than having a rigid torch, you actually hang the torches on cables. And that's all well and good, it's worked, and there's a lot of machines that are doing that, but they're inherently unstable. And so they're so unstable that you have to run stringer beads. And what we found was, the name of the game in welding is deposition rate, because the more pounds you deposit per hour, the more quickly you finish a part. So I don't care about your travel speeds or anything else. I care about how many pounds are you depositing per hour. So if you double the deposition rate and you're using a thin bead like this, that means you have to double the surface speed. Well, the problem with Inconel is it oxidizes. And so if you're running very fast in order to achieve your productivity rates, you're outrunning your inert gas shielding. And the problem with that is you get some oxides on that first layer. And that's not really much of a problem, except, as you can see here, we're making 2 layers. This is a requirement in the industry because they want to have sort of the reassurance that you have 2 layers. They want the thickness and such. And the first layer welds beautifully, but the second layer has problems if we have oxidized the first layer. So what's the solution to this? This is our solution, is rather than stringer beads, we oscillate the torch. So you can see now the same weld, which required 6 beads, is a single bead now, which reduced our travel speed by a factor of 6, which eliminated our oxidation problem on that first layer. It's a simple solution, but if you have a cable-based system, it's simply not practical to oscillate because the cables are too easily disturbed. So we had to run a rigid torch. And our rigid torch will reach into these parts. We actually have 2 torches in there because we're making 2 layers. We're doing the first layer and then the second layer. But it's the oscillation that worked. And although it seems pretty intuitive now, this wasn't intuitive to us until we went into the lab and started to weld. And like I said, as we began to push our deposition rates up to achieve the productivity that we needed, that's when we noticed the oxide problem. And that's when the light bulb went off. The other problem with this approach, or this process, is it's extremely difficult to inspect these welds. You're trying to inspect a weld that's 20 foot down inside a 5-inch diameter. Hard to do visually, hard to do with ultrasonics because the dissimilar materials cause confusion in a lot of the ultrasonic inspection. And so you're having to be reliant upon the process being extremely reliable. And when you create oxides in the first layer, it tends to create non-fusion in the second layer. And these defects, which sometimes go all the way down to the base metal, were very, very difficult to detect. So not only were we able to achieve higher deposition rates, but we're able to improve our quality to a point where we could reliably assume that we had good weld quality inside these parts. And we went on to develop inspection systems also. But once again, if we hadn't gone into the laboratory and discovered this oxide problem, we wouldn't have designed that first machine with the capability of oscillation, and we wouldn't have solved this problem. So what's the lesson here? Question everything. Sometimes if you want to be extremely productive, you need to change the rules to allow yourself to do that. In this case, it was oscillation. I hope this was a benefit to you. I look forward to seeing you again on the next episode.